Hi, let's now study applications of the optimal power flow calculation. In this lecture, we study selected types of optimal power flow problems, essentially the economic dispatch and the reactive power dispatch. Besides, important aspects to choose solvers that can tackle these optimal power flow problems are discussed. The economic dispatch forms of an optimal power flow problem seeks the most cost-efficient allocation of generation while maintaining system feasibility. The objective function represents the total generation cost, typically modeled as the sum of cost functions of all generators, reflecting full or operating expenses. The problem is governed by technical constraints. Equality constraints enforce power balance, like total generation equals demand, possibly including losses, while inequality constraints represent operational limits, such as generator capacities, ramp rates, and network limits. In addition, search-bound constraints define the minimum and maximum allowable values of decision variables, restricting the feasible region. The solution vector consists primarily of the active power outputs of generators and in extended formulations possible voltages or reserves, and set points of controllable assets, which are adjusted to find the least cost operating point that satisfies all constraints. The reactive power dispatch form of an optimal power flow problem focuses on optimally controlling reactive power resources to improve system performance, typically by minimizing power losses, voltage deviations, or enhancing voltage stability. The objective function reflects these goals, such as reducing active power losses or keeping bus voltages close to desired levels. The problem is subject to technical constraints. Equality constraints are the reactive and active power flow equations, ensuring network balance, while inequality constraints include limits on bus voltages, generator reactive power outputs, transformer tap settings, and shunt compensation devices. Search-bound constraints define the allowable ranges of control variables, restricting the optimization to feasible operating limits. The solution vector typically includes generator voltage set points, reactive power outputs, transformer tap positions, and shunt capacitor or reactor settings, which are adjusted to achieve the desired system performance while satisfying all constraints. Different solvers can be applied to the optimal power flow problem. For instance, a conventional optimization solver, like the interior point method or sequential quadratic programming, tackles the optimal power flow problem through a structured iterative procedure. First, the problem is formulated mathematically, defining the objective function, decision variables, and equality and inequality constraints. An initial feasible or non-feasible solution is then selected. At each iteration, the solver linearizes or approximates the nonlinear problem, for instance, via gradients, Hessians, or quadratic subproblems, and computes a search direction that improves the objective while respecting the constraints. This direction is used to update the solution, and supplementary routines, like constraint handling, can be applied. Example routines are barrier functions, like for interior point method, or active set strategies, like for sequential quadratic programming. The process repeats progressively, improving feasibility and optimality until convergence criteria are met, for instance, small constraint violations and negligible objective function improvement. Overall, the method systematically navigates the feasible region using mathematical approximations to efficiently reach a locally optimal power flow solution. Alternatively, a heuristic optimization solver, including meta and hyperheuristics, approaches the optimal power flow problem through a flexible, iterative search that does not rely on exact mathematical gradients, making it suitable for complex nonlinear and non-convex formulations. The process typically begins with initialization, where a single candidate solution or a set of candidate solutions is generated within the defined bounds. Each solution is evaluated using the optimal power flow objective function, while constraints violations are handled via penalty functions or repair mechanisms. The algorithms then apply heuristic rules, also known as search operators or movement rules, to explore and explore the search space, generating new candidate solutions. Throughout the iterations, solutions are selected and updated based on their performance. Balancing exploration, that means searching new regions, and exploitation, that means refining good solutions, in meta-heuristics, this process is guided by a specific strategy, evolutionary or swarm-based, while hyperheuristics operate at higher level by selecting or adapting heuristics dynamically. The procedure continues until a stopping criterion is met, for instance, a maximum number of iterations is reached or convergence is done, yielding a high quality, often near optimal solution that satisfies optimal power flow constraints. A simple and useful classification of optimization solvers commonly found in both open source and commercial software distinguishes between deterministic approaches, stochastic-based techniques, and stochastic learning approaches, based on how they explore the solution space. Deterministic solvers like linear, nonlinear, or integer programming grading-based methods follow a predictable rule-based path from a given starting point. For the same input, they always produce the same output, typically converging efficiently to a local or global, if convex, optimum. Both might struggle with not convex or high complex problems. Stochastic-based techniques like heuristics and meta-heuristics incorporate randomness in the search progress. They explore multiple regions of the search space and are more robust to nonlinearity, non-convexity, and multimodality, often finding good near-optimal solutions, but with no guarantee of exact optimality and with variability between runs. Stochastic learning approaches like unsupervised or supervised learning or surrogate-assisted optimization extend stochastic methods by incorporating learning mechanisms. They adapt their search strategy based on past experience or data, improving efficiency over time and enabling better handling of expensive or high-dimensional problems. In short, deterministic refers to precise and repeatable, whereas stochastic refers to flexible and exploratory, and learning-based refers to adaptive and data-driven. This concludes our video, where you have learned about how to define and tackle applications of optimal power flow optimization. Thank you for watching.